Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the longest increasing subsequence. This is a really difficult question, mainly because we can solve it in two different ways. The first one is actually of medium difficulty. It's kind of a standard dynamic programming problem or solution. But the second way of solving it is really difficult. It's really difficult to understand, let alone come up with in an interview setting. But it's really important to understand it, I think, because it can teach you a lot. And so we're going to be covering it in this video. Now, the question basically gives you an array of integer values. I've got an example in front of me here, 5, 7, negative 24, etc. And I've written, by the way, in green the indices of this array, just so we have them for later on. And it asks you to write a function that will return the longest increasing subsequence in that array. Now, a subsequence is defined as a set of numbers, in this case, that you will obtain by removing other numbers and keeping the remaining numbers in their given order. And so here, the longest increasing subsequence is going to be this array here that I've written in purple, negative 24, 2, 3, 5, 6, 35. And you'll notice that these numbers are not necessarily adjacent in the input array, right? We've got 24 or minus 24 here. Then we skip a couple numbers and we've got 2 and 3. Then we skip another number and we've got 5, 6, 35. So let's dive into the first way of solving this problem, which I said is of medium difficulty. So we're going to be using dynamic programming, and we're going to be building two arrays to help us solve this problem. The first one is going to be an array that we're going to call lengths. And this array is going to be of the same size as our input array. So actually, I'm going to move this here. And so it's going to be of the same size as our input array. And at each index I of this lengths array, we are going to store the length of the longest increasing subsequence that we can form with the last number in that increasing subsequence being the number at index I. So in this first index here, at index 0, we're going to store the length of the longest increasing subsequence that we can get that ends with the number 5 that's stored at index 0, and that only uses numbers that come before this index in the array. So in this case, we're only using 5. Then in the second index, we'll say, what's the length of the longest increasing subsequence that ends in 7 and only uses the numbers 5 and 7, and so on and so forth, okay? And we're going to use each of these solutions, or each of these values that we store here, to help us build out this array. Now, the second array that we're going to be building is going to be an array called sequences. You can call it sequences or indices, whatever you want. This array here, at each index, it's going to store the index of the number that comes before it. So in other words, let's take index 1. So here, index 1, we've got the number 7. Here in our lengths array, we're going to store the length of the longest increasing subsequence that ends in 7 and only uses numbers that come before index 1. And here in sequences, we're going to say, what is the index the index of the number that comes before 7, before the longest increasing subsequence that ends at index 1. And so we're going to store all these indices in this sequences array. And this sequences array is going to help us build up our final longest increasing subsequence. So this is going to be a lot clearer as we start building this out. So let's start with the first index, right? At the first index, at index 0, which we've written here, we've got the number 5. So we can say, okay, 5 is a number. So right now we've got presumably a longest increasing subsequence of length 1 that we can put here. And now we can say, are there any numbers that come before 5, or before rather index 0? No, there aren't, right? Because this is the first index in our array. This is the first value in our array. So there's nothing that comes before it. So we're done. The longest increasing subsequence at index 0 is going to be a subsequence of length 1. And what do we put here in our sequences array? Well, we can put just like the none value, because there's no number that comes before 5 in this longest increasing subsequence, so we store just none as an index, and this kind of tells us the subsequence ends at this point. Okay, fair enough. Now we get to the second index, index 1. We have the number 7. So we start iterating through all the numbers that come before index 1. There's only one in this case, the number 5, but so let's look at 5. We say, is 5 less than our current number 7? It is. It is less than our current number 7. So if it's less than our current number 7, that means that 7 could be part of the longest increasing subsequence that is created by taking the longest increasing subsequence ending in 5 and adding 7, right? So what was the length of the longest increasing subsequence ending at 5? It was 1. 1 plus 1. Why are we plus 1ing? Because we're adding the number 7, which adds one number, one length. 1 plus 1 is 2, so here we can store a length of 2. We can create a subsequence of length 2 that ends in 7. Okay, so now what do we put in sequence at this index? Remember, this sequences array here stores the previous index, or the index of the previous number, the number that comes before our given number. So here, well, we said that 5 will come before 7 in this longest increasing subsequence of length 2. So here we can store the index 0. Okay. Now we move on to our negative 24. Okay, at index 2. So what do we do with this number? Well, we say, let's look at all the numbers that come before index 2. So let's look at number 5 and number 7. Is number 5 less than negative 24? No, it's not. Okay, so we just skip this value. We know that negative 24 could not come in an increasing subsequence where 5 is the last number, right? So let's look at 7. Is 7 less than negative 24? No, it's not. So similarly, we cannot put negative 24 after 7. So here we have a longest increasing subsequence of length 1, which is the negative 24. And we can, again, put in the sequences thing, none, because there's no index there's no number that comes before negative 24, so we don't put an index, we just put none. So now you can already kind of get the idea that in this lengths array and in this sequences array, we could actually initialize some values. Here, I'll write them in brown. We could initialize this array to hold only the value 1. Because at the beginning, at the very least, at each index, we can create a longest increasing subsequence of just the number of that index, meaning an increasing subsequence of length 1. So here, I guess I'm going to initialize this array to a bunch of 1s. And let me just spread these numbers out a bit more so that they fall kind of right under our input array. Okay, so now we can put a bunch of 1s. 1, 1, 1, 1, 1, 1. And here, in our sequences array, we could initialize this to a bunch of none values. I'm not going to put that right now just because it would take a long time to write none a bunch of times, but you get the idea. So now let's move on to our fourth number, 12, which is stored at index 3. And so we can start iterating through all the numbers that come before index 3, 5, 7, and minus 24. So is 5 less than 12? Yes, it is. So whatever longest common subsequence or longest increasing subsequence ends with 5, we can put 12 at the end of it. So what was the length of the longest increasing subsequence ending in 5? It was 1. 1 plus 1, which is the number 12, gives us 2. 2 is greater than our 1 that we have here. So we can erase it and tentatively put a length of 2. But now we move on to our 7. 7 is less than 12. Yes, it is less than 12. That was like an affirmation. And what was the length of the longest increasing subsequence ending in this 7? It was 2. 2 plus 1, if we add 12 to this longest increasing subsequence, gives us 3, and 3 is bigger than 2. So here we can put 3. Now wait, before I put 3, I skipped a step. Below in the sequences array, and I guess let me erase this and rewrite it a bit better. Here we could have tentatively put index 0, right? Because when we stored 2 here, we were saying we can form a longest increasing subsequence of length 2 that starts with the number 5 and ends in the number 12. So the number that comes before 12 is 5, and it's stored at index 0, so we would put tentatively 0 here. But now we just determined that we can add 12 to the longest increasing subsequence ending in 7, because that would give us a length of 3. And in that case, the number coming before 12 is 7, which is stored at index 1. So now here we're going to not store 0, but instead 1. And now we move on to the last number, negative 24. Negative 24 is also less than 12. But if the longest increasing subsequence ending in negative 24 had a length of only 1. And 1 plus 1 is 2, which is less than 3. So we don't want to do anything here. We don't want to update this value because we've already found the longest increasing subsequence ending in 12. It's of length 3, and it points to the index 1. So let's erase this 3 and 1 and put them in purple. 3 and 1. So you kind of get now the formula. I'm not even going to write the formula down because it's pretty simple, right? The formula is, at any given number, now we're at the number 10, we iterate through all the numbers that come before it, and we check, is whatever number we're iterating through less than our current number 10? If it is, try to see if we were to add that length stored at that index plus 1, if that would be better than the current length that we have. And if it is, then we update the length and we update the sequences array. So now let's kind of finish building out this array, these two arrays pretty quickly so that we get to our solution. So we're at the number 10. We iterate through all the numbers before it. 5 is less than 10. What do we have at index 0? We have a longest increasing subsequence of length 1. 1 plus 1 is going to be 2. So here, whoops. Wait, what did I undo? Whoops, okay. So here we can store tentatively 2 and tentatively 0, pointing to the index 0. Then we get to 7. Is 7 less than 10? Yes, it is. So what do we have at 7, or at index 1? We have the number 2, a longest increasing subsequence of length 2. 2 plus 1 is 3. So we can tentatively store, whoops, why am I erasing that? We can tentatively store 3. And here we can tentatively point to index 1. Now we move on to negative 24. Negative 24 is less than 10. Yes. Here we have a longest increasing subsequence of length 1. 1 plus 1 is 2, but 2 is not greater than our 3 here, so we don't want to update that. Then we get to 12. 12 is greater than 10, so we cannot put 10 at the end of the longest increasing subsequence that ends in 12. So we found our solution here. We can erase this and put them in purple, 3 and 1. Now we move on to the next point, 2. At 2, we iterate through all the numbers that come before 2. 5. Is 5 less than 2? No, it's not. Okay, don't do anything. Is 7 less than 2? No, it's not. Okay, don't do anything. I'll just pause for a second. Why aren't we doing anything? Well, we cannot put 2 at the end of a longest increasing subsequence that ends in 5 or 7, because 2 is not greater than 5 or 7. Now we get to minus 24. Minus 24 is less than 2. What was the length at minus 24? It was 1. 1 plus 1 is 2. 2 is greater than 1. So we can tentatively store 2. And here we can tentatively store as an index 2. Why are we storing 2 in the sequences? Because minus 24 is at index 2. And then 12 and 10 are both greater than 2, so we skip them. So here we can actually write them in purple. So we had 2 and 2. All right, now we get to the next point, 3. 5 and 7 are greater than 3, so you skip them. Minus 24 is good. So minus 24, we're going to tentatively put 2, because we have 1 here. And we're going to tentatively put 2 here. We're pointing after 3, we point to minus 24, which is at index 2. Then we have 12, 10. Both of these numbers are greater than 3, so we skip them. And then we get to the number 2. 2 is valid because 2 is less than 3. So what did we have stored here? We had a longest increasing subsequence of length 2. 2 plus 1 is 3. 3 is greater than 2, so we can put 3 here, and we can point to the index where 2 is stored, which is 5. So now here we can store the number 5. Awesome. We're left with only 4 numbers. We're almost there. So we get to this 12. 12, okay, 5 is less than 12. So here we can tentatively put 2. Here we can tentatively put 0. But then 7 is less than 12. So, okay, we have to erase this 2. Now we can put 3. And here we can put 1, right? So now this is going to become a lot of work to keep updating this. Then we have negative 24 is less than 12. So negative 24, we've got 1 plus 1. That's 2. 2 is not less than 3, so we don't update anything. 12 is not strictly less than 12, so we skip the number 12. Then we get to the number 10, and at the number 10, what do we have? We've got 3, right? So 3 plus 1 is 4. So 4 is greater than 3. So we can put 4 tentatively. And we can point here to what index? Index 4 as well. So here we can tentatively point to index 4. And then we get to 2. At 2, we've got a length 2. 2 plus 1 is not greater than 4. And then here we've got the number 3. Here we've got 3. 3 plus 1 is equal to 4. 4 is equal to 4. So here we've got 2 equal subsequences. So we could update it. We could update it if we want to take the most recent longest increasing subsequence. I guess I'll just update the index here. And here I'll just write this in purple. 4. And here we're going to say before 12, we're going to point to 3. So we've got index 6. So I'm going to take a quick break here just to make sure we're on the same page. What does this mean? What do these two values mean? It means that at this index, index 7, we've got a longest increasing subsequence of length 4 that ends in the number 12. The number before 12 in this longest increasing subsequence originates from index 6, which is the number 3. Then here at this index, we've got the number that's stored at index 5 that comes before it. At index 5, we've got the number 2. And then here, the number before it is stored at index 2, which is negative 24. And before negative 24, we've got none. So we've got no numbers. And so we can keep building this array, and you'll see that we eventually get to our solution where here, I guess I won't go through building this entire array, but here this would be something along the lines of, I think, 5 and 6, right? And then at 35, yes, 5 and 6. And wait, how many numbers do I have here? We were at number 12, so then we get to here. We've got 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 8, 9, 10. So here this would actually be 4, 5, and 6. And then here we would be pointing to index 6, 8, and 9. If we were to continue building these out and applying the formula that we were applying, this is what we would get. And so now, I'm not going to go through how we got these 3 numbers because it would have been too tedious and too long, but you've gotten the idea at this point. And now we can backtrack through our sequences array, and we can find our longest increasing subsequence. We start here. We say, okay, we've got the number 35. So we store 35. Then what comes before 35? Well, we go here. We point to the number stored at index 9, which is 6. So we have 6. Then here we point to the number stored at index 8, which is 5. So we store 5. Then we go to index 8. We take the number stored at index 6, which is 3. So we store 3. 3 points to the number stored at index 5, which is 2, and so on and so forth. Now we get to what I just said before when I went through the example, and we finally get to minus 24, which is our solution. Awesome. So this is the first algorithm. This is the first way of solving this problem. And before we dive into the second, much tougher solution, let's just quickly analyze the space-time complexity of this algorithm. In terms of space, it's going to be pretty straightforward. It's going to be space is going to be O of n. Why O of n? And what does what does n represent? N represents the length of our input array. O of n, because we're building 2 arrays of the same length, n, as our input array. So O of 2n, drop the 2, O of n space. In terms of time, we are going to be taking O of n squared time. Why O of n squared? Well, because we're iterating through the array once, through the input array, and at each point in this array, we're reiterating through all the numbers that come before it. Okay? So remember, at the number 5, we iterate through no numbers. At the number 7, we iterate through the number 5. At number minus 24, we iterate through 5 and 7, etc. So that gives us a time complexity of O of n squared. And if you're still not convinced, remember, at each of these iterations, all we're doing is checking, is the other number less than our current number? And if yes, is the length plus 1 greater than or equal to our current length? So we're doing like a constant time operation at each point. And then building the sequence at the very end, we're just backtracking through our array, and that's at most going to take O of n time. So this is our space-time complexity analysis for this algorithm. Awesome. Now, is there another solution? Well, yes, there is. I told you at the beginning. And is it a lot tougher? Yes, it is. Why do we want to do this solution? Well, because it turns out it can greatly optimize our algorithm. How can it optimize it? Well, I'll tell you. It's not going to optimize the space complexity, but it's going to optimize the time complexity. And this is one of the first times that I'm actually going to give you the target time complexity before we actually go into the algorithm. I'll explain it to you as I erase all this stuff that I've written. This new algorithm is going to have O of n space, just the same as this one, but in time it's going to have O of n log n instead of n squared, okay? N log n. So already there are logs involved, which you can kind of tell you that it becomes a bit more difficult. And let's just dive immediately into how this works. So let's erase the time. O of, let's put it in purple, n log n. And let's move this and make it smaller and bring it to the top. All right, awesome. So for this algorithm, for this solution, we are going to be building two arrays, just as we did before, but they're going to be a bit different, okay? One of them is going to be called sequences, and this one is actually going to be identical to our sequences array from before. But then we're going to be building an array that I'm going to call indices, and this one is going to be different. This array is going to store, at each index I, it's going to store the index, okay, the index of the last number in the longest, or rather in an increasing subsequence of length I. Meaning, let's say we're at index 3, right around here. Let's say that this is index 3 right here. Here, we're going to store the index of the number in our input array that comes at the end of the longest increasing subsequence of length 3. But we're not just storing the index of any number, we're storing the index of the smallest number that can come at the end of a longest increasing subsequence of length 3. And it's going to be important that this be the smallest number that can end that increasing subsequence. And I'm going to tell you why in a little bit as we dive into it. But so, how this algorithm is going to work is we're going to iterate through our array, just as we did in the previous algorithm. But then, instead of kind of doing a double for loop and iterating through all the numbers that come before it, we are going to use binary search somehow. Okay, right now you might be thinking, whoa, how are we going to be using binary search? Well, we're about to find out, but that's what we're going to be using. And so that can kind of already hint at you why this time complexity is going to turn into O of n log n, right? Because if we're iterating once through the array, that's O of n, and then in each of those iterations, we're somehow applying binary search. Binary search has a time complexity of log n, right? And so that's going to turn into O of n log n. But so, at each iteration, we're also going to have a variable that we call length. And this length is going to be basically what is the longest increasing subsequence that we've come up with thus far. What's the length of the longest common subsequence or increasing subsequence that we've come up with thus far? And so this is going to start out at 0, right? Because at the beginning, we just don't have an increasing subsequence. So we just initialize it at 0. And the sequences array can also be initialized to a bunch of none values, like in the previous example. And the indices array is also going to be initialized to a bunch of none values. Okay? And so we start iterating through our array. Start at the number 5. 5 is the first number, so we kind of just say, okay, we can build a longest increasing subsequence of length 1 that ends in the number 5, right? So we're going to say indices at index 1, which is the length of the longest increasing subsequence that we can make, is going to be the current index that we're at, which is 0. So here, we're going to say, let's store 0. Or I guess I can write this in purple. Let's store 0. So let's take a quick break for a second. What does this mean? We're saying at this index here, which is 1, the index here is 1, right? The longest increasing subsequence of length 1 ends in the number 5, which is stored at index 0. Okay? And in our sequences thing, we're going to say, well, at index 0, right before index 0, there's no number, so we just store none. This sequences array represents the exact same thing as the sequences array did in our previous solution. And so now we can update this length here to 1, because the longest increasing subsequence that we have so far has length 1. Okay, great. So far we haven't applied binary search yet. In the algorithm we would have, but here when we're doing it kind of intuitively and trying to explain it conceptually, we haven't applied binary search yet. So now we get to this 7. Okay. For the 7, we are going to say, where could we store, like, what is the longest increasing subsequence that we've found in this indices array, that we've stored in this indices array, that could end in 7? In other words, we want to find the greatest number that's smaller than 7 that ends an increasing subsequence. And so here we can just look, we say, okay, we've only stored an increasing subsequence of length 1 that ends in the numbers stored at index 0, which is 5. So let's just look here. Okay? Here, what does this represent? This represents the number 5. 5 is smaller than 7. There's nothing else to look at. So therefore, we can store at the index that comes right after it, we can store 1, which is the index of the number 7. And so that means that here, at index 2, here this is index 2, we have an increasing subsequence of length 2 that ends in the number stored at index 1, which is 7. And the number that comes before 7 is 5 in this increasing subsequence. So here, instead of storing none, we can store 0, the index of that number, which is 0. The index of the number 5 is 0. And so now we can update this length to 2. Okay, so now we get to the number -24. We still haven't really seen how binary search fits into all of this, but it's going to start to make sense. And rest assured, this is going to make also a lot more sense when we actually go through the code implementation. But so we've got the number -24. So we want to find the greatest number that is smaller than -24 that ends an increasing subsequence so that we can see where we can put -24. So let's look at both of these numbers here. We've got index 0 and index 1 stored in this indices array. Index 0 represents 5. Index 1 represents 7. I'm not going to apply binary search yet. I'm just going through it kind of intuitively. 5 and 7 are both greater than negative 24. So that means negative 24 cannot come in an increasing subsequence after 5 or 7. And those are the only two options we have. So that means we can only have an increasing subsequence of length 1 that starts and ends with negative 24. Okay? So what do we do? Well, what we're going to do is we're going to update here. Instead of storing 0, I just erased 0, we're going to store 2 now, which 2 represents negative 24. Because remember I mentioned earlier, and I said this was going to be important, and I'll reiterate it here, at each index in this indices array, we want to store the smallest number that can come at the end of an increasing subsequence of length I, where I is the index that we're at. So here at index 1, longest increasing subsequence of length 1, what do we want to store? We want to store the smallest number that can be at the end of this longest increasing subsequence. And the smallest number thus far between 5, 7, and minus 24 is minus 24, and it's stored at index 2. So we put index 2. All right. Now we get to 12. So for 12, we find the greatest number that is smaller than 12. So the greatest number that is smaller than 12 and that ends an increasing subsequence. So we look at both of these options that we have here. 2 and 1. 2 points to minus 24. 1 points to 7. Oh, and by the way, I forgot to update. I forgot to update here instead of a dot dot dot. Let me erase this a tiny bit. Here instead of dot dot dot, we want to put none, because we're saying at index 2, the thing that comes before it is none. And here the length stays 2 because we didn't come up with a bigger subsequence. So now we've got, or a longer one. Now we've got 12, 7, and 20. We're looking at 7, which is stored at index 1, 7, and negative 24, which is stored at index 2. 7 is greater than minus 24, so 7 is the greatest number that's less than 12, and that ends an increasing subsequence. So 12 can come after 7, right? So we can put here the index where 12 is at, which is 3, okay? And we can say here 12 is going to point to 1, right? Because 7 is at 1, and 7 is the number that's going to come before 12. Okay, so now you might be starting to see patterns, and it's going to make a lot more sense as we go into this fifth number, 10. It's going to make a lot more sense. But here, we just don't forget to update the length to 3, because that's the longest increasing subsequence that we've got now of length 3. So now we get to the number 10. Let's apply binary search. How are we going to apply binary search? Well, we're going to say, in this indices array here, we've got 3 values so far. And of those 3 values, we want to see, where does this 10 fit in? So we're going to start by taking the middle value. The middle value, because we've got 3 values, right? And so the middle value, 1, we say, what is stored at index 1? It's the number 7. Is 7 less than 10? Yes, it is. Therefore, because 7 is less than 10, anything that comes before this 1 here, we can just ignore. Why can we ignore it? Because we know that 7 is less than 10. So 10 can come after 7. We can add to this increasing subsequence that ends in 7. We can add the number 10. And anything that comes before it here is going to be a smaller increasing subsequence because these indices represent lengths. So anything that comes before, we just ignore. And we've just eliminated half of our indices array that we're searching. And that's how we apply binary search, you see. So here, we just ignore this entire part because 7 is less than 10. And so we say, now let's move on to the right side. Let's look at the right side of here. And so there's only one point. There's this 3. What is stored at 3? The number 12. 12 is greater than 10. So that means that we cannot put 10 after 12, right? And here we're done because there's nothing that comes after this 3, right? So we can just say, okay, 10 must fit kind of somewhere here, right? And what's going to end up happening is we're going to say, well, we know that at this index, we've got a longest increasing subsequence of length 2 at index 2 that ends in 7. 7 was the greatest number less than 10 that ended a subsequence. So we can have an increasing subsequence of length 3, so it would be stored here at this index, index 3, that ends in 10. And 10 is smaller than 12, so we just overwrite this. We overwrite this 3 here to be 4. Okay? And so now at index 4 in our sequences array here, we're going to point to the number that comes before here, 1. So here, let's take a quick break. Why did I say the number that comes before here? Well, this is an increasing subsequence of length 3. And this is an increasing subsequence of length 2. So naturally, the number that ends here comes right before the number that ends here. So since the sequences array is kind of a pointer array, right? All these numbers are pointing to previous values. Well, we can say at index 4, the number that comes before the number at index 4 is the number stored at this index, which is 1. And so we put 1. Okay? So now we move on to the next number, 2. We've got the number 2. Let's apply binary search again. The middle, we've got 3 possibilities. We look at this middle value. Got 1. What number is stored at index 1? It's the number 7. 7 is greater than 2. And since we know that here at each of these indices, we store the smallest number possible, right? And we overwrite these numbers when we have the opportunity. Like here, remember, we were storing index 3 with the number 12, but we overwrote it with index 4, where we have the number 10. So 7 is greater than 2. So we know that anything that comes after here to the right is going to have a number that's greater than 7. So here, anything that comes here, we can eliminate it because 7 is greater than 2. And so here again, we're applying binary search to eliminate half of our indices array. So now all we have to do is look at the left of this here. Turns out we only have 1 point. So what does this point to? It points to index 2, which is the number negative 24. Negative 24 is less than 2. Therefore, the greatest number less than 2 that ends an increasing subsequence is the number 24. And it's a subsequence that's stored here at index 1 of length 1. So we can create a subsequence of length 2 that's going to end in 2. And it's going to be negative 24 followed by 2. And so here, instead of 1, which is where the 7 was at, we can overwrite it with the index where 2 is stored, which is index 5. And so here we're going to put index 5. And here at index 5, we're going to point to index 2, which is where the 24 is at. So far, we don't update our length because we still only have longest increasing subsequence of length 3. All right, so now we get to the 3. Apply binary search again. Start at here. Okay, we're at 5. We've got the number 2 stored at index 5, right? Number 2. 2 is less than 3. So anything that comes before this, we just ignore. Right? Because we know that we can put 3 after 2. And any subsequence that comes here to the left is going to be smaller than the subsequence ending at 2. So now we look at this point that has 4. 4, there's the number 10 at index 4. 10 is greater than 3. So we want to fit this 3 right around here. So we're going to create an increasing subsequence of length 3 that ended in 2, but we append 3 now, and we overwrite this 4, which was where 10 was at, and we put index 6, right? And what does 6 point to? Well, it points to the number right before it, which is stored at index 5. So here we've got 5. And here the length is still 3. Okay, now we get to the number 12. We've got still 3 values to look at. So we start at the middle one, 5. At 5, we've got 2. 2 is less than 12. So we ignore everything that comes before it. We look at here, 6. We've got 3. 3 is stored at index 6. 3 is less than 12. So we move up, and now we're out of values to compare, but so here we can just store 7. We can store a new longest increasing subsequence. We're not overwriting anything. Store index 7. Then we point to 6 here, right? The number right before it, 6, which is where 3 is at. And then we can update our length to 4. And then you can see how we can keep applying this formula, and we're going to end up coming to the same solution. So here, let's actually try going through it. We get to this 5 now. 5, we start in the middle, so we've got 4 values, right? In binary search, how do you get the middle value? You take the start index, which in this case is going to be 1, right? This is going to be the start index, 1. This is going to be the end index, which is going to be 4, right? 1, 2, 3, 4. You sum them up. 1 plus 4 is equal to 5. 5 divided by 2 is 2.5. You round that down. So our middle index is going to be 2. So we're going to start at the middle index here, 2, where we've got the number 5. So what's stored at number 5? Index 5 is 2. 2 is less than 5, our current number. So we can ignore everything that comes before it. So now we look at here. We have 2 values. With binary search, we sum up these 2 indices and then we divide them by 2, and we would be looking at this number 6 here. And so what's stored at number 6? It's the number 3. 3 is less than 5. Okay, so we can ignore everything that comes before 6. Let me just undo both of these here. Everything that comes before 6 we ignore. Now we get to the number 7. At 7, we've got the number 12. 12 is greater than 5. So we want to store our 5 somewhere here. What does that mean? It means that here we had an increasing subsequence that ended in 3, and it was of length 3. And now we can add 5 to that increasing subsequence to get one of length 4. we can overwrite the one that we have of length 4 right now that ends in 12. We can overwrite it and put the index of our 5, which is 8. And so here we've got 8, and 8 is going to point to 6, the number that comes right before it. Great. Now we get to the number 6, the before last number. So we start again at this index, right, with binary search. What's stored at 5? It's 2. 2 is less than 6, so we ignore everything that comes before it. Now we go here. 6, we've got 3. 3 is less than 6. Okay, so we ignore everything that comes before this. Get to this 8. At 8, we've got the number 5. 5 is less than 6 as well. So we ignore everything that comes before this. Turns out we're just creating a new length. So here we're just going to store 9. And 9 is going to point to 8. So here we're going to store 8. All right. And so finally we get to this 35. Oh, now we have to erase this and say that our longest increasing subsequence has length 5, because we've got 1, 2, 3, 4, 5. Get to this 35. Take the middle value between these two, between all of these. So 1, 2, 3, 4, 5. We start at index 1, end at index 5. So sum 1 and 5 together. 1 plus 5 is 6. Divided by 2, 3. So we're going to start smack in the middle at index 3. What is stored at index 3? 6. What is stored at index 6? 3, the number 3. 3 is less than 35. So everything that comes before this, we just scratch out and ignore. Now we move on to this point here, because we're left with 2 points. We start with this one with binary search. At index 8, we've got the number 5. 5 is less than 35. So we can ignore everything that comes before it. And then we get to the final point, 9. At index 9, we've got the number 6. 6 is less than 35. So we can ignore everything that comes before 9. And we can create a new length here that ends at index 10. And that points to index 9. And our final length is going to be 6. All right. And so now if we want to build up our array, we just start by saying, okay, we end with 35. And we end with the number stored at length 6, which is 10, which is 35. And then we backtrack through our sequences array. At index 10, we've got the number 9. At index 9, we've got 6. Then at index 9, we've got the number 8. At index 8, we've got 5. Then at index 8, we've got 6. At index 6, we've got 3, and so on and so forth. And we keep backtracking, and we can build up our increasing subsequence. And so here, to reiterate one last time, we iterate through our array of length n, and at each iteration, we apply binary search on our indices array, which can have, theoretically, up to length n. And so our time complexity becomes n log n, and space complexity doesn't change. So this is a really tough algorithm. I hope that you were able to understand it. Perhaps the code walkthrough will make it a lot clearer, so let's dive into it. All right, so we've got our longest increasing subsequence function defined. It takes in an array of integer values, and we're going to start with the solution that was kind of medium difficulty, the one that we covered first in the conceptual overview. So recall that we were building 2 different arrays, right? We were building a sequences array that was going to store kind of the indices that we were going to use to build up our final longest increasing subsequence. And then we were building a lengths array that was going to hold the longest, or the lengths of the longest increasing subsequences ending with the numbers stored at each index, right? So we can initialize our sequences array to just hold none values, none for x in array. And we can initialize our lengths array to hold just 1 for x in array. Why do we store 1 here? Well, because the longest increasing subsequence that we can theoretically create at each index is at least 1, right? Just that number. The length is at least 1. And so then we're going to say for I in range len of array. We're going to iterate through our array. We're going to say our current number is going to be equal to array of I. And then we're going to start reiterating through all the numbers that come before it. So we're going to say for j in range 0 all the way till I, exclusive, other num is going to be equal to array j. And so now we check, is the other num less than our current num? If it is, then we can add our current num to potentially to an increasing subsequence. So if other num less than current num, and here we want to be strictly less than, right? Because that was the prompt. The prompt told us that we want a strictly increasing subsequence. So if other num and current is less than current num, and then we can check if the length that's stored at index j, right, the length of the longest increasing subsequence ending with the number other num at index j plus 1 is greater than or equal to the length that we currently have stored at index I, well, then we update it. And here, why do I have less than or why do I have greater than or equal to? I could remove this greater than or equal to. I could remove like the equal to. I'm just using it because that way we get kind of the last longest increasing subsequence in the array, if that makes sense. We're kind of overwriting as we go through it if we have, two longest increasing subsequences of the same length. But here you can kind of ask your interviewer what to do in such an example. But so if this condition is satisfied, then we update lengths of I to be equal to lengths of j plus 1. And on top of that, we update our sequences array to point to other num, right? Or rather to point to the index that other num is stored at, which is j. And then here we can return, we want to build our sequence, right? So we can return, we're gonna create a function called build sequence, and that function is going to take in probably our array, right? Our array of numbers. It's going to take in our sequences array, because that's this array, the whole purpose behind this array is to build up our sequence. And it has to take in the last number in our greatest subsequence, right? Or maybe the index at which our greatest subsequence is stored, our longest increasing subsequence is stored. But you'll notice that here we didn't really keep track of that, because we have this lengths array, but for all we know, the longest increasing subsequence might be in the middle of the array. And so what we can do just to simplify things here is we can declare here a number or a variable max length idx, and we can initialize it to 0. And so here what we're saying is we're saying at the beginning, the longest increasing subsequence ends at index 0. Okay? And so here, in our first for loop, once we've finished iterating through all the numbers, we can say if the current length that we've stored at index I is greater than or equal to the length that's stored at max length idx, then update max length idx to I. And that way here, we can directly return max length idx, pass it in to this build sequence. We know that at this index, we have the longest increasing subsequence, and we have the last number, or the position of the last number in our longest increasing subsequence. And so now we can build up we can define our build sequence function, which takes an array, sequences, and an index, a current IDX, which starts out as max length IDX. We can declare our sequence, our final sequence, to be an empty array, and we can say while current IDX is not none. Recall that we initialized our sequences array to none values, because once we reach none, that means they're nothing. There's nothing else, right? If a number points to none, that means that no number comes before it. But so while current IDX is not none, we append to the sequence array of current IDX, and then we say current IDX is going to be equal to sequences current IDX. And then we can return the reversed sequence because we built it from the back. Now, what are we doing here? Well, we're saying at each iteration that current IDX is not none, add to our sequence the number that's stored at our current index, which is stored, in sequences, and then say the next current index is going to be the index stored at sequences of current index, right? That's how we kind of backtracked through the array during the conceptual overview. Cool, so this is the first algorithm. This runs in O of n squared time, and it runs in O of n space. Build sequence is just an O of n time function, and these two for loops here are going to be O of n squared. Otherwise, we're only building two arrays of length n, so this is pretty clearly O of n squared time and O of n space. Awesome. So now let's dive into the second solution, the really tough one. And this solution, believe it or not, is actually going to use the exact same build sequence function. It's just this first part here that's going to be different. So let's duplicate it. Let's comment this out, and let's start working on this. So I'm just going to delete all of that. And for this, we're gonna also have a sequences array. So I guess I could have kept the first line of our function, because that is going to be the exact same. We initialize our sequences array to none for x in array. And remember, that represents the exact same thing as it does, or as it did in the first solution. But then we have this indices array, right? Indices, which is going to be initialized to none for x in range. And here, the range is going to be length of array plus 1. Why is it that? Well, because recall that at each index in this indices array, at each index I, we're storing the longest increasing subsequence of length I. And so we want to have potentially a longest increasing subsequence of length n, where n is the length of the array. And so basically, at index 0 in this indices array, we're always going to store none. We're not using anything at index 0. Okay, that's why we're creating this array to be of length len array plus 1. All right, and so then finally we have our length variable, which represents the length of our current longest increasing subsequence. And so then we can say for I num in enumerate array. We enumerate through our array. We want to keep track of the index that we're at, which is I. We want to keep track of the current variable, of the current number that we have, which is num. Depending on your language, you might just have to say, num equals array I. In Python, you can just do this enumerate thing. So here, this is where we're going to apply binary search. So we're going to say new length. The new length of our increasing subsequence is going to be equal to binary search of, and so binary search is going to take in what? Well, binary search takes in a starting index, which is going to be 1 in this case, and I'll tell you why in a second. Then it takes in an ending index, which is going to be length. I'll tell you why in a second as well. Then it takes in indices, because we're going to be looking at we're going to be doing binary search in this indices array. It's also going to take in our input array because we're going to have to actually look at the numbers in our input array. And it's going to take in the current number that we're looking at. Okay. So what just happened, right? Why are we, what is this? What are all these parameters? Why do we start at 1, etc.? Well, recall what we just said. Our indices array represents subsequences of length I, where I is the index in this indices array. And we said that the value at index 0 is always going to be none, because we don't have an increasing subsequence of length 0. Even though we kind of initialize it at 0, it's going to quickly be overwritten. Okay, so we only want to start doing our binary search starting at index 1. And if you recall in the conceptual overview, that's where we were starting. Remember, we were looking at like 3 values or 4 values, and they always started at index 1. And then the final index, the end index in our binary search, is going to be the length of the longest current increasing subsequence, which is the final index that we have in indices that doesn't have a none value, right? And it turns out that at the beginning, that end index is just length, because we have nothing in this indices array. So here, it's actually, at the beginning, it's actually 0, right? But we put length. So now, before I do everything else that needs to occur here, right, I'm just going to pass for now, and we're going to write our binary search function. So let's define binary search. Binary search is going to take in a start IDX, an end IDX, our indices array, our array, and a number. And it's going to say, if start IDX is greater than end IDX, then we return start IDX. This is kind of the base case of binary search, right? If we're at a point where our start IDX is greater than our end IDX, then there's no more like searching to do. So we just return start IDX. Otherwise, we can declare our middle IDX, the middle point that we start at, right? Which is start IDX plus end IDX divided by 2. These 2 slashes in Python 3.5 just mean that we're also rounding down the answer. So if you were doing this in JavaScript, you'd have to do something like math.floor start IDX plus end IDX divided by 2. You basically, yeah, the 2 slashes are the equivalent of math.floor, which means rounding down. Cool. So now you can say if array of indices of middle index, I'll explain what that means in a second. If that is less than num, then start IDX is going to be equal to middle IDX plus 1. So what does this mean? Well, recall during the conceptual overview, we said at any point we were looking, okay, what does we're at middle index in our indices array. So indices array at middle index contains a number which represents itself an index in our input array. So what is the number stored at that index? Well, it's the number array of all of this. Is that number less than num? If it is, then we ignore everything that comes to the left of it, because we know that we can have an increasing subsequence where we put our number after the number stored here, and anything that comes before it in the indices array represents an increasing subsequence of a smaller length. So we ignore it. So we say start IDX is going to be equal to middle IDX plus 1, right? We ignore everything to the left of it. Otherwise, end IDX is going to be equal to middle IDX minus 1. Because remember, because we're overwriting every time we're overwriting points and we're storing the smallest number that can come at the end of an increasing subsequence of length I, we know that here, if our number here is greater than num, then we know that we can ignore everything that comes to the right because it's just going to be greater than that. Okay? And so here we can return binary search of start IDX, end IDX, indices, array, none. We can recursively call binary search. And that's that. That's our binary search, right? And so here, when we hit the base case, we return our start IDX. And so let's just look at the very beginning here. When we call new length, at the beginning, we call new length with length 0, right? Whoops. With a start IDX of 1 and an end IDX of 0. And so we get into binary search. We immediately hit the base case. Start IDX, which is 1, is greater than end IDX, which is 0. So we return start IDX, so we return 1. So here, we have new length equals to 1 at the very beginning. So what do we do after that? Well, we're going to say, okay, sequences of I is going to be equal to indices of new length minus 1. And then we're going to say indices of new length is going to be equal to I. Why are we doing these two things? Well, we know that the length of our the position at which we want to put our current number is going to be new length, and that's also going to turn out to be the length of our new increasing subsequence ending with this number. So we can say indices at index new length is going to be equal to I. It's going to point to the current index that we're at. And the number that comes before that, which we want to store in sequences of I, is going to be the number located right next to it. Indices of new length minus 1, right? So here new length is 1. So at sequences of I, we're going to store indices of 1 minus 1, which is 0, which is going to be none. Because when we have an increasing subsequence of length 1, what comes before it, there's no number that comes before it, so it points to none. And lastly here, we can say length is going to be equal to maximum of length and new length, right? Because we want to update our length, which is the length of our current longest increasing subsequence, and this, remember, gets passed into our binary search function as the end index, the end IDX. And so that's that. Now we can get out of this for loop and we can return the same thing, build sequence, the same thing as our previous algorithm, array, sequences, and then instead of this max length IDX here, what's going to be the last number? Well, the last number is going to be stored at indices length, right? Because length is our maximum, the maximum length of our increasing subsequences. And at the end of this for loop, we've got this length that's our maximum value. And so we find the number, the index that's stored at indices of length. And then we can just get into our build sequence and start building everything from there. And so this is going to run in, it's going to run in O of n space again, right? That's we said that at the beginning because we're building, again, two arrays of length n or n plus 1. So it converges to n. We're not storing anything else in arrays or variables. We'll just have this length variable. The build sequence is identical. So that's going to be O of n space. However, the time complexity is going to be O of n log n. Why O of n log n? Because we're iterating through our array of length n. And at each of those n iterations, we are applying binary search. And binary search is going to run in log n time on the indices array, which has length n, right? And then everything else after that is just constant time operations. We're just updating values and comparing two values to determine which one is greater. So there you have it. The longest increasing subsequence algorithm that runs in O of n log n time. It's a really difficult algorithm. As I said at the beginning of the video, it's definitely exceedingly hard to come up with this in an interview. You would most likely not be expected to come up with it in an interview. it's really difficult, but it's really cool. It's really interesting to understand how it works because you might be able to apply this to other problems and you might be able to impress an interviewer that way. And it really teaches you also how binary search works, I think, and how you can apply binary search in non-obvious places, non-obvious implementations. That being said, the first solution, this one is definitely one that you would be expected to find in an interview. So be sure to understand that. It's pretty similar to a lot of other dynamic programming questions that we have here on the website. And that's that. I hope this video was helpful. I'll see you in the next one.